Now that we have an introduction to acids and bases, Ka and Kb, we can take our knowledge from grade 11, we can add it to the mix of what we know, and we can take weak acids and weak bases, combine all of this together. What we're able to do is look at titrating a weak acid or a weak base using a strong acid or a strong base. Example, 20 milliliters of sodium hydroxide is titrated with 10 mils of acetic acid at 0.3 moles per liter. Determine the concentration of sodium hydroxide and the pH of the final solution. The most important thing you can learn in chemistry is that when you have a problem, you have to solve it in a methodical way. Our gut reaction might be to look at the numbers and divide something out and come up with a quick solution. It's not going to get us where we need to go. You have a big problem, you need careful steps to solve it. Here, that careful first step is the chemical equation. Sodium hydroxide reacts with acetic acid to give us water and sodium acetate. We're using the AC for acetate. That's no problem. Textbook, I can't remember which way they go on that. It doesn't really matter. We do know, though, is that we have a certain amount of information given. In grade 11, we used our stoichiometry chart to provide us with a bit of direction when solving a problem. The first step in our stoichiometry chart is to fill in what we know. We know that we have 0.02 liters of sodium hydroxide and 0.01 liters of acetic acid. We're also told that the concentration of acetic acid is 0.3 moles per liter. We need to determine where to go. Well, we know that we need to find the concentration of sodium hydroxide. Concentration sodium hydroxide. So right here is our target. How do we get there? Well, we know information between the acetic acid column and the sodium hydroxide column can only be shifted in the mole row. So we work our way up, look at the mole ratio if applicable, and then solve using moles and volume. This works out pretty well because we find out that we have 0.003 moles over here. The ratio is 1 to 1, 0.003 moles over here, leading us to 0.15 moles per liter as the concentration. In grade 11, we would have said the final solution had a pH of 7 because we have a salt water solution.
Eller så må jeg faktisk bare velge å legge alle de pengene i hendene på Martine Lund og velge å stole på.
Det som gjør meg usikker på å slippe kula eller ikke, det fordi jeg har hørt av folk.
Både Isabel og Alex, så jeg frykter litt at den kula hennes kan dette i bakken.
En av oss må vinne. Det samme hvem som vinner. Og så skal vi slippe kula, så slipper vi kula, så deler vi det. Og vi slipper kula med en gang, og så deler vi det opp når vi kommer hjem. Så vi får 150 her. Jeg lover at om jeg vinner, så slipper jeg en kula, og så skal jeg dele med deg, Isabel. Jeg stoler ikke på Kevin, og derfor må jeg slippe en kula. Selvfølgelig var jeg bestevennen til Jørgen, det deler du bare.
Fy faen!
However, you're looking at this now, and my suspicion is that you're seeing the sodium acetate here, and you're thinking to yourself, I know that acetate is an ion that's going to interact with water. We've seen this with quinine, we've seen this with acetate, we've seen this with ammonia. They interact with water, and when they interact with water, they rip off a hydrogen, producing a base and regenerating acetic acid and our hydroxide. Right away we look at this and we notice that our acetate ion is acting as a base. It's producing hydroxide. We're going to need a Kb value to figure out what's happening here. In fact, we even know the pH of our final solution is going to be greater than 7 because of the presence of hydroxide. So we have a neutralization, and we're looking for the presence of a salt that interacts with water. That weak acid ion is going to be what does that. The acetate ion will do that. Oxalic acid. In fact, any of the acids you've seen in biology, if they're in their unprotonated state, they're going to interact with water and they're going to create a basic solution. So at this point now, we've identified that we have an acetate ion interacting with water that's going to change the pH and make it greater than 7. The problem, though, is we don't know the Kb for acetate or for acetic acid. We do, though, know that the Ka from the back of our book or from a previous question is 1.8 times 10 to the negative 5. This is important because we also know that Kw equals Ka times Kb. Therefore, the Kb for acetic acid can be calculated as 5.6 times 10 to the negative 10. Take a minute and add that to your notes. Try the calculation. Make sure your writing is legible, and then we'll move on. So using the power of technology, I shifted over my Kb calculation off to the side there. We know that it's still true, and I'm pretty sure you know what's happening right about now.
These are the things I see right in front of me. As I open my eyes, oh, I give thanks to life.
So now that we have our ice table, we can fill in the information we know. Let's start with water. Nothing's going on there. We then have our acetate ion concentration, which is the first part of our equation. So to figure out that concentration, we need to look at our previous table and see what's happening over here. So at this point here, we now have a sodium acetate solution. So let's fill in these values. So we know that our sodium acetate solution is going to have 0.003 moles. We also know that the volume of the solution is going to be the sum of the volumes that were mixed together. So 0.03 liters. Therefore, the concentration that we have at equilibrium, when it balances, is going to be 0.1 moles per liter. Now, one other little thing to address here. I did mention that this line was referred to as an equilibrium. Realistically, though, I shouldn't have referred to it as an equilibrium. I'm going to get rid of that right now and put it back as just being a regular forward reaction arrow. It does happen in reverse, but it's not even worth discussing because the percentage is less than 99%. We'll also add our 0.1 here to keep our work complete. And of course, this value here is the one that ends up over there. So now we can work with our concentrations. We're going to assume that we don't have any base to start with. And we're also going to safely assume we don't have any acetic acid. And the reason for this is this reaction here went to completion. Even number of moles, all the acetic acid is used up. Because the acetic acid here is used up, there is none left over, and this becomes the driving force of determining pH. If any acetic acid would remain, because it ionizes much more readily than this will interact with water, this here, the acetic acid, would be the determining factor for pH. Change. Well, this is going to have to lose because this side is 0, so it must gain. And then we have our 0.1 minus x, x, and x. So far everything is on track. we can now take a look at what happens when we put this into a KQ expression. Now, in your notes, if you've already started working on this, which I hope so, you would have called this KQ expression KB. KB is going to be products HAC times hydroxide divided by the concentration of the acetate ion. We have a numerical value for Kb. We figured it out a few minutes ago, and that was 5.56 times 10 to the negative 10. All that is equal to x squared divided by 0.1 minus x. Now, the minus x that's over here, I haven't written. So the question is, what happened to this minus x as it went down there? And what happened there is the small x assumption, or the 100 rule. So take a minute and look at that. Again, that's the initial concentration divided by the Ka. In this case, initial concentration of 0.1 divided by the Kb. Answer is far greater than 100. We can see that just by the size of the Kb here. Being on the denominator, that number would be in the millions. So the amount that breaks off is really, really going to be negligible. This is beautiful for our math because suddenly our x value is really just a square root again, multiplied by the 0.1. And our x value is 7.45 times 10 to the negative 6. Working our way down with that, that is the same as our hydroxide concentration. Once we have the hydroxide concentration, we can find out that our POH is 5.15. Therefore, our pH is going to be 8.87. This is the example that's seen on page 600 in your textbook. It's rather insane. It goes over about half a dozen pages. Now that you've seen the basis of it, take a look at the example on page 600 and work through it. Unfortunately, there's one little tricky part in that example, and that has to do when they're at halfway to the equivalence point. At that point, then, they have a 0.03 value, which is the same for the multiple concentrations. It gets a little bit confusing. Take your time with it. Hopefully, you're looking at this early in the morning instead of really late at night, and you'll be just fine.